Okay, so we're now going to start to learn how to use the half angle identity to find the exact, not a calculator rounded value, but the exact. So remember what I said, that if it says exact value, the unit circle is involved. So first of all, you're going to look at the note sheet and you're going to see that the half angle, see theta divided by 2, is equal to positive negative depending on which quadrant, right? Which quadrant the half angle will end up in. It's the square root of 1 subtract cosine theta. So that's the whole angle. This is the half angle. We need to know what the whole angle is divided by 2. So let's think about it this way. I have this pie divided up into 6 pieces. And if I divide each of those pieces in half, we have half pieces, right? So if I start right here, 1, 2, 3, 4, you guys can do the math already. 4, 5, 6, 7, 8, 9, 10. Oh, so 1/12 is half of 1/6. So 23 pi 12ths is exactly 1/2 of 23 pi 6. So the theta is 23 pi 6, but what we care about is where would that be on the unit circle, right? Because that's usually the theta that we're talking about, the coterminal. So if this is 12 pi 6, if you go around the circle again, this is 24 pi 6. 23 pi 6 would be down here. Half of that, half of an angle in the fourth would be maybe in the second or third quadrant. Let's see, 181. Nope, would probably be in the second quadrant, I'm going to guess. 181 plus 1, yeah. Because anything in through here, when you, when you half this, it would almost have to be in quadrant 2. Okay, in quadrant 2, sine is positive, but we'll know in just a minute. So we have to find what theta we're talking about. We're talking about 23 pi 6. Well, that happens to be the same as, looks like, 11 pi 6, because it's down in this quadrant right here. So that's the theta that we're going to use when we plug it into there. So sine of 23 pi 12ths is equal to the positive or negative square root of 1 subtract cosine. And I'll go ahead and put 23 pi 6, but I know that I'm using the 11 pi 6 coterminal divided by 2. Well, cosine down there at 11 pi 6 is root 3 over 2. So cosine of 23 pi 6 is positive root 3 over 2. Well, look at what we want. I know this is going to be very annoying for you guys, but since this has a denominator of 2, I'm going to rewrite this with it having a denominator of 2. And I do not want to have this fraction over this 2. So we're going to do this. I should have made it bigger. I'm going to write this 2 as 2 over 1. And then we're going to multiply top and bottom by 1/2. So up here, we have 2 subtract root 3 all over that agreed upon 2. So when we multiply this denominator by its reciprocal 1/2, that goes away. And now what we have left is, now I'm going to have to erase all this beautiful stuff right here. Dang it. Well, I mean, it wasn't that beautiful, but positive, negative. So this becomes 2 subtract root 3 over 4, but we can take the square root of 4. The square root of 4 is 2, so now the 4 comes out, and now there will be a fraction out of the radical. So it will be 2 subtract root 3. This is exactly how we know where, this is so silly of me that I even, so if this is 12 pi twelfths, this would be 24 pi twelfths. So right here, we're in the fourth quadrant, and in the fourth quadrant, sine is negative. So this is a negative value. So sine of 23 pi twelfths is equal to negative root 2 subtract. So root, all of this underneath the radical sign, 2 subtract root 3, and all of that now not under the radical, outside the radical, all over 2. All right, we'll probably do another one of those. So let's see if I have another one. Yeah, I do. I'll do a cosine. So if you look at your note sheet, the cosine formula. Okay, so cosine theta over 2. Ooh, theta, not pi. Theta over 2 is equal to positive negative root in the numerator 1 plus cosine theta all over 2. So 7 pi eighths, well, if this is 8 pi eighths, right about here is going to be 7 pi eighths. So we know that we're looking in the second quadrant, cosine is negative. So we're going to choose this negative value right here. But 7 pi eighths, remember, 7 pi eighths is 1/2 of 7 pi fourths, right? So 7 pi fourths will be the theta that we use, and 7 pi fourths actually happens to be on the unit circle, which is cool because right there we can see cosine value is positive root 2 over 2. The sine is the negative value. So we can get started. We can choose the negative 1 plus cosine theta divided by 2. Well, that's negative 1 plus root 2 over 2 all over 2. And we're going to rewrite this 1 as 2 over 2. And now we can rewrite that whole thing as these share the denominator now. Now it's 2 plus root 2 over 2. That's this piece. All over 2. So I'm going to put that over 1. And now I'm going to multiply denominator and numerator by 1/2 so we can get rid of that. And now what we have is negative we have 2 plus root 2 all over 4, but the square root of 4 is 2, so it will actually go on the outside of the radical. So only the numerator will now have the radical. So 2 plus root 2 all over 2, because the square root of 4 is 2. So cosine 7 pi eighths is equal to square root 2 plus root 2 all over 2. And that's what this value would be right here. So that x value right there, wow, we'd need a bigger parentheses, would be negative 2 plus root 2 all over 2. I don't know what the sine value would be at 7 pi eighths. All right, that's it for a half angle identity, I believe. Well, actually, I will add one other thing. Tangent, when you get to the tangent ones, the tangent has either 2 or I think it has 3 different versions. So hopefully that will, okay. So tangent theta divided by 2, it has a weird square root version. it also has, so if you simplify this and you multiply by the conjugate, you also have this version, sine theta over 1 plus cosine theta. However, there's a third version. Tangent theta is equal to 1 subtract cosine theta all over sine theta. I believe this is the easiest one to use. You don't have to worry about the square root, and you don't have to worry about multiplying by the conjugate because there's only one term in the denominator. So if you have a half-angle trig, you might want to consider using this version. All right, that's it for this one.